Section 3.4 is about the chain rule. The chain rule allows us to differentiate a composition of two functions, and the chain rule says that the derivative of a composition is the derivative of the outside function composed with the inside function times the derivative of the inside function. So in this example right here, we have y is equal to 3x squared minus 5x to the ninth. So our inside function is g of x equal 3x squared minus 5x. And our outside function is f of x equal x to the ninth. So in this case, we know that the derivative of the outside function is 9x to the eighth. And we know the derivative of the inside function is 6x minus 5. So basically the chain rule is telling us that y prime is equal to 9. I insert the inside function and I multiply by the derivative of the inside function. So that's our derivative according to the chain rule. Now the next thing I want to introduce is something called Leibniz notation. With Leibniz notation, we let the inside function be equal to the variable u. Therefore, y is equal to f of u. And I can write my derivative now using Leibniz notation. So the derivative of y with respect to x is equal to the derivative of y with respect to u. So that represents this part, times the derivative of u with respect to x. So that represents this part of the chain rule. Notice how these kind of like, it seems like they kind of cancel, but across the diagonal they match up. Okay, I'm going to start off by doing some easy examples. So here my function is y equal cosine x raised to the 5th power. It's just notation. So according to the chain rule, my derivative is 5 times the derivative of the inside function, which is negative sine x. Okay, if I clean this up a little bit, I get y is equal to negative 5 sine x cosine to the 4th. In WebAssign, make sure to use parentheses around your inputs. Second example here, my inside function is 3x. My outside function is e to the x. So according to the chain rule, h prime of x is equal to the derivative of my outside function with the inside function plugged in times the derivative of the inside function, which is just 3. This is a common derivative, and so you'll note that in general, anytime you're taking the derivative of e raised to some constant k times x, this is always going to give you k times e to the kx. Here we have sine of 7x. This is my inside function. Y prime is given by cosine of 7x times the derivative of the inside function, which is just 7. So y prime is 7 cosine 7x. And this is like the previous example. In general, if you had y equals sine of k times x, then y prime would always be equal to something. Okay. Next, I want to do some examples that are a little more complicated because we have to use the chain rule with the product rule or quotient rule. So here you see I have a product of two functions. For this function, I have to use the chain rule. Same with this function. So I'm just going to call this f and this g. So the derivative, I'm going to take the function, the first function, and I'm going to multiply by the derivative of the second function using the chain rule right here. And then I add the second function times the derivative of the first function using the chain rule. And that's what I get. So I'm going to simplify a little bit. I see that there are two major terms here. And I'm going to factor out, let's see, I can factor out 8 of these. And I can factor out one factor of 3x minus 5. Here I have a 2 and I have a 3, a 9 and a 4. So it seems like I can factor out a 6. And let's see what that leaves me in the first term. I have 4x plus 7. And that looks like it all. Now I'm going to go and see what I can factor out from the second term, or what's left. Looks like I have 3x minus 5. There's 36 here, so there's a factor. I factored out the 6 is the GCF, so I have a 6 here. And that's pretty much all that's left. So rewriting that, I have, let's see, 7, this will give me 18, 19, 20, 22x minus 30 plus 7 minus 23. And now this is completely factored. Okay, so here's my derivative. Now let's go and do the second example. So here I have an example where I'm definitely going to have to use the quotient rule here. But if you look at the bottom function, you'll notice that I need to use the chain rule because 8x is inside of my exponential function, and then this function is inside of the square root function. So this is actually more than one composition. So let's use the quotient rule. So I'm going to use the derivative is f prime times g. So the derivative of the top times the bottom minus the top function times the derivative of the bottom, and then over the bottom function squared. So here I have y prime is equal to the derivative of the top, which is 2x, times the bottom, which is the square root of 7 plus e to the 8x, minus the top function times the derivative of the bottom function. So I'm actually going to, this one might get a little bit messy, so I'm going to take it over here, and I'm going to say my bottom function g of x is equal to root 7 plus e to the 8x, which can be written in this form. Okay, so the derivative g prime of x is 1/2. So here I'm using the chain rule. And then I have to multiply this by the derivative of this function, which is e to the 8x times 8. So canceling these, I get 4. And I get that my derivative is 4e to the 8x over the square root of 7 plus e to the 8x. Okay. So going back here, the derivative of the bottom function is 4e to the 8x over the square root of 7 plus e to the 8x. And I had to use the chain rule twice there, once for this function and another time to take care of this other outside function. And don't forget the denominator using the quotient rule. We take 7 plus e to the 8x and we square it. So that's my derivative. I'm going to clean it up a little bit. And what I'm going to do is, I don't like having fractions inside of fractions, so I'm going to multiply by this denominator so I can clear it. And that's going to leave me with 2x times 7 plus e to the 8x minus x squared times 4e to the 8x all over 7 plus e to the 8x. Now this is going to be to the 3/2 power, because this power here is just 1, and this is 1/2. So I'm just going to cube this. Okay, so it looks like I can factor out a 2 and an x so far. That's going to leave me with 7 plus e to the 8x. And minus, I'm going to have 2x e to the 8x all over 7 plus e to the 8x to the 3/2. And I think I'm going to stop there. I think that's pretty much as I can do. Okay, next, I'm going to do some examples that require more than one application of the chain rule, because we have a composition of a function inside of a function inside of another function. So here my outermost function is sine, and then inside of it I have another sine with another sine, and then finally x squared plus a squared inside. A squared is just a constant, so, just treat it like that. We're taking the derivative with respect to x. So what I do is, if I have multiple compositions here, what I'm going to do is I start with the outermost function. So I have y prime is equal to cosine. And then I leave the inside part as it is. So this is going to be sine of x squared plus a squared. But then according to the chain rule, I need to take the derivative of the inside function, which happens to be this function. But this function is also a composition. So I start with the second outermost function, and I take the derivative of this function. So I get cosine of, now there's my new inner function. But then, of course, according to the chain rule, I have to take the derivative of this function. So the outermost function of this function is sine. So I get cosine of x squared plus a squared. And then, of course, I have to take the derivative of the inside function again, which is 2x plus 0. Okay, so this is my derivative. So again, when you have multiple compositions, I usually start with the outside function and start applying the chain rule there. And then I move to the next outermost function, and then the next outermost function, etc. Okay, so just to kind of recap what happened here, my outermost function was sine x, and then I had, the next function was also sine x, the next function was also sine x, and then maybe I'll call the other innermost function x squared plus a squared. So y prime in this case was f prime of g of h of m of x times g prime of h of m of x times h prime of m of x times m prime of x. So you can see here I'm using the chain rule 1, 2, 3 times. Here's one more consequence of the chain rules. We can actually compute the derivative of the exponential function with base 9. So here's y equal 9 to the x. What is the derivative of this function? Well, we don't know at this point. But here's a new rule for us, and that's the derivative of the exponential function with base a is equal to, the function itself times the natural log of a. Okay, so for example, we have the derivative of, 4 to the x is just equal to 4 to the x times ln 4. And why is this true? I'm just going to give a quick sketch here. Well, the exponential function can be rewritten as e to the ln 9 to the x, just by properties of inverse functions here. And then, of course, we have law number 3 of logs. This can be written as x times ln of 9. This is just a number, by the way. And we know that whenever we have the exponential function, we talked about this in the beginning, we can easily take the derivative of this function. So I'm going to do y prime is equal to ln 9 times e to the x ln 9. But remember, this was equal to this, so I get 9 to the x. Okay, so just using properties of logs, we're able to show that the derivative of this function is equal to this. I'm just going to do a quick couple examples. So here I have exponential function with base 3. The derivative is just going to be 3 to the x times ln of 3. And like I said, this is just a number. Here we have another example. We've got multiple compositions. My outermost function is 2 to the x. Middle is 5 to the x. Innermost is x squared minus 1. So I'm just going to start with the outermost function and use the chain rule twice. So in this case, y prime is equal to, well, I know that the derivative of this guy is 2 to the x ln 2, but I need to plug in my inside function, which is this sort of complicated thing, times ln 2. Now I need to take the derivative of the inside function, which is going to be 5 to the x squared minus 1 times ln 5. And then I need to take the derivative of the inside function here. It's just 2x. Okay, so you can clean this up a little bit. You'll get 2 ln 2 ln 5 x times 2 to the 5 to the x squared minus 1 times 5 to the x squared minus 1. And that's our derivative here. Oops, there it is.